When I first learned mechanics, pretty much every problem started with forces. Draw the object, draw the force arrows, add them up, and then use F is equal to ma. Once you get used to that routine, it pretty much feels like that's the only mechanics that can be done. Then, usually, somewhere up in an undergrad mechanics course, Lagrangian and Hamiltonian mechanics show up. At first, they can look like two more complicated ways of getting an answer Newton already gave us. So I want to take one problem we already know, a mass on a spring, and actually work through all three methods. With Newton, we start with the restoring force. With Lagrange, we build the Lagrangian from kinetic and potential energy. And with Hamilton, we track the position and momentum together. The spring moves the very same way every time. What changes is the information we start with and the steps we use to get the equations of motion. Newton gives us the most familiar route, right? Lagrange can make the coordinates and constraints easier to handle. Hamilton turns one second order equation into two first order equation and gives us a useful picture in the phase space. None of them is replacing the other here, and it's not a contest to find the smartest formulation. For this ideal oscillator, all three give exactly the same prediction. I mainly want to understand what each method is doing and why we would even bother learning all three. And because the spring mass system is so simple, we could focus on methods without the example getting in the way. Consider a block of mass m attached to an ideal spring with spring constant k. The block moves horizontally on a frictionless surface. We choose the equilibrium point as x is equal to 0, and we measure the displacement on the block with the coordinate x. If we pull the block to the right and release it, the block accelerates towards the center. It passes through equilibrium, compresses the spring on the other side, slows down, reverses, and repeats. For this ideal system, there is no friction and no loss of mechanical energy. The motion continues forever. The displacement is sinusoidal or cosinusoidal. If the block is released from rest at x is equal to a, then the position can be modeled by x cosine omega t. Where omega is just the spring constant divided by m, and you take the square root of it. We are going to derive the same curve 3 times. That may sound repetitive, but it lets us compare the methods without changing the physical problem halfway through. The Newtonian perspective asks what forces are acting on the mass and what acceleration do they produce. The Lagrangian perspective asks what happens if we start with the kinetic energy minus the potential energy and use the Euler-Lagrange equation. The Hamiltonian perspective asks what happens if we describe the motion using position and momentum at the same time. Same oscillator, same prediction, but 3 different calculations. Let's start with Newton, since this is probably the most familiar version. When the spring is stretched, it pulls the mass towards equilibrium. When the spring is compressed, it pushes the mass towards equilibrium. For an ideal spring, Hooke's law says that the force is proportional to the displacement. F of s is equal to negative k, which is a constant, times the position. The minus sign just tells us the direction. If x is positive, the force points in the negative direction. If x is negative, the force points in the positive direction. Either way, the spring pushes or pulls the mass back towards equilibrium. Newton's law says that the sum of forces is equal to the mass times the acceleration. For the horizontal spring, the spring force is the only unbalanced force in the direction of motion. Therefore, m double dot is equal to negative k of x. Rearranging gives that. And then we defined omega squared, which is equal to k over m. And the equation becomes x dot plus omega squared plus x is equal to 0. This is the equation of simple harmonic motion. The logic is very direct. The position tells us how stretched or compressed the spring is. That gives us the force. The force gives the acceleration. The position changes. The force changes too. So the calculation updates from one moment to the next. This is the basic Newtonian change for this problem. The differential equation tells us that the acceleration is always proportional to the negative of the position. X double dot is equal to negative omega square x. So therefore we need a function whose derivative or whose second derivative is the negative of itself apart from a constant factor. Sines and cosines have exactly that property. So therefore the general solution is x of t times a, which is the amplitude cosine omega t, plus a phase constant. The initial velocity and the initial position determine the two constants. If the mass begins at x is equal to a and is released at t is equal to 0, then phi or phi is 0. So therefore x of t is a cosine omega t. The velocity is x dot of t is equal to negative a omega sine omega t. And the acceleration is x dot dot of t is equal to a negative squared cosine omega t, which is just equal to, again, negative omega squared times x of t. At maximum displacement, the velocity is 0 and the restoring force is largest. At equilibrium, the force is 0, but the speed is the largest. The mass overshoots because reaching 0 force does not mean reaching 0 velocity. This is why Newton's method feels so intuitive here. We could watch the force arrow grow, shrink, and reverse. We could also see why the mass accelerates towards equilibrium but keeps moving when it reaches the center. Now, let us solve the same problem without starting with the force diagram. Lagrange begins with kinetic and potential energy of a system. For the ideal mass spring system, the kinetic energy is 1/2 m dot x squared and the potential energy stored in the spring is 1/2 kx squared. The potential forms a parabola. The equilibrium position sits at the bottom. Moving away from the equilibrium in either direction stores energy in the spring. Lagrangian mechanics combines the two scalar quantities into a new function. For our oscillator, the Lagrangian is 1/2 m dot squared minus 1/2 kx squared. The work field in the title needs a quick clarification. The Lagrangian is not a physical field in space like the electric field. I am using the word loosely because L assigns one number to every possible pair of x dot. In other words, we choose a possible position and a possible velocity, plug them into the Lagrangian, and you get a number. We can do that with whether or not the mass actually has the position and the velocity during the motion we are studying. So the starting point has changed. Newton asked us to list the forces. Lagrange asked us to choose coordinates and write down the energies. For this one-dimensional oscillator, the coordinate x is obvious. In a more complicated system, the coordinates do not need to be ordinary Cartesian positions. They can be angles, distances along curved tracks, or any other variables that describe the system's possible configurations. This is one reason Lagrangian mechanics is useful for systems with constraints. We can choose coordinates that already follow the allowed motion instead of solving for every constraint force separately. Our spring only has one obvious coordinate, so we do not get the full benefit yet. Now draw the position of the mass as a function of time. If we fix a starting point and an ending point, we could sketch as many possible curves x of t between them. Some are smooth, some wiggle, and some take a ridiculous detour. Most of them are mathematically possible curves, but they are not the motion the spring actually follows. For any one of these proposed paths, Calculate the Lagrangian along this curve and integrate it over the time. That number is called the action. The physical path makes the action stationary. That means that a small change in the path produces no first order change in S, the action. So therefore the delta, the infinitesimal variation of the action is 0. But this is often called the principle of least action. But stationary action is more accurate. The physical path does not always give the smallest possible path. It can be a minimum, a maximum, or another stationary point. This could sound like the spring checks every possible path before choosing one. I would not take that picture literally. The practical point is that the stationary action condition gives us a differential equation. Take the Lagrangian, take the partial derivative of the Lagrangian with respect to x dot, then take the derivative of time with that quantity, and then subtract the partial derivative of the Lagrangian with respect to x and make it equal to 0. This is the Euler-Lagrange equation. And for the mass spring system, the Lagrangian is 1/2 m x dot squared minus 1/2 kx squared. The derivative with respect to velocity is partial derivative with the Lagrangian with respect to x dot is m dot, and you take the derivative with respect to that, you get x double dot. The derivative with respect to position is negative k of x. Substituting into the Euler-Lagrange equation gives mx dot dot plus k of x is equal to 0, or x double dot plus omega squared x is equal to 0. That is the exact same picture we got from Newton. We did not prove that forces are somehow fake. For a conservative system like this one, the force is still sitting inside the potential energy. F is equal to negative d of v over dx is equal to negative k of x. The difference is simply where we started. Instead of writing down the force first, we wrote down T minus V, which is, or the potential minus, the kinetic minus potential, and applied the Euler-Lagrange equation. The approach becomes specifically useful when symmetry enters the problem. Noether's theorem tells us that the Lagrangian stays unchanged under a continuous transformation. There is a conserved quantity. Hamilton makes one more change to how we set up a problem. The Lagrangian is written using position and velocity x and x dot. Hamilton replaces the velocity with the momentum conjugate to x. For an oscillator, the momentum is equal to m dot x. That makes the switch from velocity to momentum. We defined the Hamiltonian with a Legendre transformation. The Hamiltonian x of p is equal to the momentum x dot minus the Lagrangian. Because x dot is just equal to the momentum divided by mass, we obtain for this particular system, the Hamiltonian works out to be the total mechanical energy. Hamilton's equations are x dot is equal to the partial derivative of the Hamiltonian with respect to momentum. The force is equal to the partial derivative of the Hamiltonian with respect to x. And notice how there's a negative sign there. For the oscillator, they become x dot is equal to the momentum divided by mass, and the force is equal to negative k of x. Newton's gave us the second order equation for x. Hamilton gave us two first order equations that work together, one for x and one for momenta. The first tells us how the position changes. The second one tells us how momentum changes. It's a different setup, but it should still describe the same equation or the same motion. Differentiate the first Hamilton equation with respect to time. Then use the force, negative k of x, which is just the derivative of respect to the momentum with time. And we get x dot plus omega squared is equal to 0. So Hamilton has passed the first test. It reproduces Newton's equation. The real payoff, though, is what happens when we plug x and momenta together. In ordinary space, the mass just moves left and right along a line. But position by itself is not enough to tell us what happens next. At x is equal to 0, the mass could be moving right or moving left. The position isn't the same, it's the same in both cases. But the next part of the motion is different. We need the momentum too. So we put x on the horizontal axis and p on the vertical axis. This plot is called the phase space. At any moment at one point, x momenta tells us both where the mass is and how much momentum it has. Conservation of energy requires us that the momentum squared over 2m plus 1 half kx squared is equal to the energy. This is the equation of an ellipse in phase space. When the mass is at maximum positive displacement, x is equal to a, and momenta is 0. As it moves towards equilibrium, x decreases and the magnitude of its momentum grows. At equilibrium, x is equal to 0 and the momentum has its largest magnitude. The spring then compresses, the momentum falls back to 0 and the state continues around the ellipse. As the mass completes one full oscillation, the point completes one trip around the ellipse. Hamilton's equations also tells us the direction and the speed of the phase space at every possible point x momenta, or xp. The velocity of the phase is equal to the velocity phase xp is equal to x dot p dot, which is just p over m, negative k of x. If we draw those directions as arrows, we get the flow field. Every possible state gets an arrow that says where it moves next. Different total energies give different ellipses, and a state stays on the ellipse by the same set by its energy. We can make the plot a little cleaner by rescaling the axis. Define capital X square root kx, and then capital P, which is going to be p divided by the square root of m. Then the Hamiltonian becomes 1 half x squared plus b squared. The equation of motion now becomes x dot omega p and p dot negative omega x. In these rescale coordinates, the simple harmonic motion looks like a rotation with angular speed omega. The same back and forth motion now traces a circle at a steady rate. This is what I mean by flow in the title. The equation does not only move the one state we happen to choose, they tell us every possible starting point in the phase space how to move. Now, place the three descriptions beside one another. Newton begins with Hooke's law and uses F is equal to ma to obtain the motion. Lagrange begins with the Lagrangian, which is the kinetic minus potential energy, and applies the Euler-Lagrange equation. Hamilton begins with the Hamiltonian, which is the sum of potential plus kinetic, and applies Hamilton's equations. And all three lead to the same ordinary differential equation, x dot dot plus omega squared x is equal to 0. Newton is usually the easiest method when the forces are easy and simple to draw. For this oscillator, Hooke's law and F is equal to ma gets us the answer almost immediately. Lagrange becomes helpful when the coordinates for constraints are awkward. Instead of solving for every constraint force, we choose coordinates that match the allowed motion and work with the difference of the kinetic minus potential. Hamilton is useful when we care about how the full state changes over time. Phase portraits, stability, chaos, statistical mechanics, and later quantum mechanics all make heavy use of this formulation. So there is no universal winner. For a basic spring, Newton is probably the fastest. For another problem, Lagrange or Hamilton may make the setup much easier. The best choice depends on what we are trying to calculate. Newton's asks, what forces act on the object? Lagrange asks, can I write the difference of the kinetic minus potential in useful coordinates? And then finally, Hamilton asks, how do position and momentum change together? This spring mass system is deliberately simple. It is isolated, conservative, and perfectly linear. Real springs have limits. Real surfaces have friction. Real oscillators lose energy. Newtonian mechanics handles friction by adding a friction force. Lagrangian mechanics can include non-conservative generalized forces, or a dissipation function if you like. Our simple time-independent Hamiltonian conserve energy, so friction takes some extra work and may require us to modify or enlarge the setup. This is worth mentioning because we could not translate between the three methods blindly. The assumptions have to match, specifically once non-conservative forces are involved. Even without limitation, the ideal oscillator is worth studying because the same mathematics appear all of physics. Near stable equilibrium, many complicated systems behave approximately like harmonic oscillators. Molecules vibrate, electrical circuits oscillate, fields can be broken into oscillating modes. In quantum mechanics, the harmonic oscillator is one of the standard systems that can be solved exactly. The Newtonian method gives us practice with forces. The Lagrangian method introduces action and makes symmetry easier to use. Hamilton introduces phase space and becomes important later in statistical and quantum mechanics. So this is just not three fancy solutions to a homework problem. The spring is simple. It's a simple place to learn tools that keep showing up later. A mass moves back and forth on a spring. With Newton, the displacement gives us the restoring force, and the force gives us the acceleration. With Lagrange, we combine kinetic and potential energy into the Lagrangian, which is the kinetic minus potential, and the Euler-Lagrange equation picks out the physical motion through stationary action. With Hamilton, we track down position and momentum together. The state moves around a closed orbit in phase space, while the energy shifts between kinetic and potential. Every method brought us back to the same equation and same oscillation. I do not think these are little three different physical worlds. It's one mass, one spring, and one motion. But after working through all three methods, I could understand why they can feel like three worlds. One is built around force, one around action, and one around motion and phase space. Forces, fields, and flow. Same oscillator, same physics, three ways to do the problem.